Welcome back to day 6 of our journey. Okay, we're diving right into this explainer today to tackle, honestly, one of the most important questions in the whole world of artificial intelligence. How does an AI model actually go from making a terrible guess to a pinpoint accurate one? I mean, so far we've explored what AI is, how machine learning works, and how deep learning adds just incredible power to the mix. But today we're unlocking the actual secret behind how these models learn. Now, what if I told you that AI improves by just failing over and over again? It completely reframes how we look at intelligence, right? When a model gets something wrong, it's so easy to think, oh, it's broken. But that is not a flaw. That is literally the learning process. AI actually gets better by making millions of mistakes, acknowledging them, and then just getting slightly better each and every time until it's completely accurate. Here's our roadmap for today's explainer. First up, the power of mistakes. Then, the core learning loop. Third, unpacking the math. Fourth, real-world house pricing. And finally, test your knowledge. We're going to break down this complex black box logically, moving from the basic feedback loop straight into the math, and then grounding it all in a real-world example so you don't feel overwhelmed. All right, let's kick things off with section 1, the power of mistakes. Feedback, loss, and error. So, whenever an AI makes a prediction, it compares that guess to the correct answer to get some much-needed feedback. If it's wrong, the model absolutely needs to know. We call this feedback loss or error. Loss simply tells the model exactly how far off its guess was. And this brilliantly illustrates the golden rule here. A bigger loss means a worse prediction, and a smaller loss, well, that means a much better prediction. Moving right along to section 2, the core learning loop, the engine of improvement. Okay, here is the exact cycle that forms the absolute beating heart of machine learning. The model starts out by making a prediction, then it checks its work by comparing that guess to the actual data, measuring the error by calculating the loss. Once it knows just how wrong it is, it tweaks its internal weights to reduce that error for next time. And then it repeats, sometimes thousands, sometimes literally millions of times. That continuous repetition is exactly how accuracy improves. Which brings us to section 3, unpacking the math, translating jargon into logic. Let's unpack the key mathematical ideas that drive this cycle behind the scenes, starting with the loss function. Simply put, this is a mathematical way of measuring just how wrong the model was. It takes an abstract mistake and turns the error into a workable number that the computer can actually process. So if the prediction is perfect, this number is tiny. But if the guess is way off base, the loss function generates a massive number for the system to handle. Now, once the model knows its loss, it has to figure out how to fix it. Enter gradient descent. This is the step-by-step process of moving in the direction that lowers the loss. Think of this like standing on a steep hill in heavy fog. You want to walk downhill to the lowest point, but you can't see the bottom. Gradient descent helps the model feel its way downhill, step by step, to find the exact direction that reduces error to its absolute lowest point. But here's where things get kind of delicate. How big of a step do you actually take in that fog? Well, that's your learning rate. It controls exactly how big each step is during gradient descent. And this setting has to be just right. If the steps are too small, the learning is painfully slow, right? It takes forever to get down the hill. But if they're too big, the model might overshoot the best solution completely and literally end up walking back up the other side of the hill. No way we want that. Finally, we have backpropagation. This is the process of sending the error backward through the network so each internal weight can be updated. This is incredibly powerful because it tells every single part of the network exactly how much it contributed to the mistake. Did the first layer cause the error? Was it the third layer? Backpropagation assigns the blame perfectly across the board, and that is exactly why neural networks can learn so effectively. Let's see this in action in section 4, real-world house pricing, making the math concrete. All right, let's ground all of these heavy concepts by applying them to a real-world scenario that we all understand, predicting real estate values. Imagine our AI model looks at a house's features and predicts the property is worth $300,000. But the actual true price of the property turns out to be $350,000. So, the crucial point here is that our loss, the exact gap the model needs to correct, is $50,000. The model is off by exactly $50,000, and it uses that specific, tangible mathematical error to figure out how to adjust its internal weights. So what happens next? The AI uses backpropagation to adjust its weights based on that $50,000 error, and its next prediction comes out to $345,000. It is now much, much closer. You see, it's not magic. It's not guessing. It is continuous correction. When you hear people say AI is smart, what they really mean is that it is mechanically just very, very good at reducing error over time.
Almost done. Let's hit Section 5, Test Your Knowledge, the core engine of AI improvement.
Before we wrap up this explainer, I want to challenge you with a quick mental exercise. Imagine your own model predicting house prices. What is the prediction? What is the actual price? What's the loss? And how would the model improve after one update? Pause for a second and actually try to answer these prompts using your own numbers. Because if you can confidently explain this loop, you truly understand the core engine of how AI gets better.
In our next explainer, we're going to explore a brand new challenge, how AI can sometimes overfit to the training data, why that happens, and exactly how to stop it. But for now, just remember that AI gets better simply by measuring its mistakes and adjusting again and again until the error gets smaller. So I'll leave you with this final thought. If true intelligence is just the mechanical reduction of error over time, how many mistakes are you willing to make today to become smarter tomorrow? Thanks for joining us, and keep on learning.